Hey guys, today we're going to look at symmetry and dilations. First, symmetry, you've got some definitions and examples here at the top, and then we're going to look at some together. Keep in mind that figures can have more than one type of symmetry. So you can have a figure with line and point, line and rotational, all three, point and rotational, or just one. So a line symmetry, a figure has line symmetry if the figure can be mapped onto itself by a reflection in a line. I think of that as you've cut the figure in half. Point symmetry, the figure has point symmetry if the figure is mapped onto itself by rotating the figure 180 degrees about a center point. That means it's the same upside down. And a rotational symmetry, figure has rotational symmetry if the figure is mapped onto itself by rotating the figure less than 360 degrees about a center point. Think of a pinwheel. So as you rotate a pinwheel, every time you rotate it just a little bit, it still looks the same. So taking a look at problem number 1, we have a hexagon. We can cut that hexagon in half this way or this way, so it definitely has line symmetry. We can rotate that figure just a little bit and it's going to look the same, which allows us to have point and rotational symmetry. Problem number 2, we have line symmetry down the bottom. Line symmetry is the easiest to me. And we also have rotational symmetry because we can take that triangle and rotate it less than 360 degrees, and it still looks the same. The rhombus that you see in problem number 3 cannot be cut in half and flipped over itself like a mirror image, so it does not have line symmetry. It does have point symmetry because we can turn it upside down and it looks the same, and we can also rotate it less than 360 degrees and it will look the same. As we look at problem number 4, we have a right triangle. We cannot cut it in half for line symmetry. We cannot look at it the same upside down, and we cannot rotate it less than 360 degrees and it looked the same. So this one has none. Number 5, we can cut it in half. So we have line symmetry. Does not have point symmetry because it does not look the same upside down, but we can rotate it and it looked the same. Problem number 6, line symmetry does not have a mirror image when we cut it in half. Point symmetry, we can rotate it and it looks the same upside down, and we can rotate it less than 360 degrees and it will look the same. Number 7 has line symmetry. We can cut it in half and it's the same on both sides. It does not look the same upside down. We cannot rotate it less than 360 degrees and have it look the same. Problem number 8 cannot be cut in half, does not look the same upside down, cannot be rotated to look the same less than 360. So this one is none. The next page is problems 9 through 20, and we will look at those together in class. You will take a couple of page turns and head over to dilations. This is the last transformation that we are going to look at. And a dilation is an enlargement or a reduction of a figure. It's either going to get bigger or it's going to get smaller. The scale factor indicates how much the figure will get bigger or smaller, and that scale factor is called K. If K is greater than 1, it will get larger. If K is less than 1, it will get smaller. So as we look at problem number 1, K is 2. So we know that figure is going to be larger. And the way that you figure out your new coordinates is you multiply the X and the Y by the scale factor. So we're going to do 2X, 2Y. So that's negative 10, 2, negative 6, 8, and 4, negative 2. And we're going to plot those new points. So negative 10, 2, negative 6, 8, and 4, negative 2. Again, I put it on the wrong side. 4, negative 2. And notice when you connect those dots, how much bigger the figure got. The figure got twice as big as the original figure. As you look at problem number 3, your scale factor is 1/2. That means you're going to take half of X and half of Y. So negative 5, 1, negative 1, 4, 3, 1, and negative 1, negative 2. And remember, this is less than 1, so it's going to get smaller. half as small, actually. And don't get too caught up on the fact of, is it inside the figure? Is it outside the figure? Does it overlap the figure? Just make sure you're doing what you're supposed to do and it will be just fine. All right, let's take a look at problem number 5. K is 5 halves. 5 halves is 2.5, which means it's greater than 1. So our figure is going to get larger. And we're going to do 5 halves X, 5 halves Y. And feel free to use your calculator if you need to. D is not too hard since 0 times anything is anything. So 5 halves times 2 cancels the 2's. So we get 5 and 10. 2 goes into 4 2 times, and 2 times 5 is 10. And then 5 halves times 6. 2 goes into 6 3 times. 3 times 5 is 15. And 2 we've already done. And then 4 we've already done. And negative 2 is negative 5. All right, so 0 0 is also D prime. 5 10 is E prime. And then 15 5 is F prime, and 10 negative 5. All right, I had to count all those out. And then as you can see, your figure is 2.5 times larger than your original. Taking a look at problem number 11, identify the scale factor. So again, you're looking from D to D prime, or E to E prime, or F to F prime. It doesn't really matter which one you're looking at. So D is 0 6, and I go to D prime, which is 0 2. So the zeros don't change, which means I need to look at, how did I go from 6 to 2? Well, from 6 to 2 is a division of 3. So your scale factor is 1/3 because you've gotten smaller. If you get bigger, then your K, or your scale factor, will be greater than 1. As always, let me know if you have any questions. This is the end of our chapter. Coming up will be our study guide and our test. You guys let me know if you have any questions.